Hello and welcome to my talk on Bayesian workflow for the PyMC conference. The case study we'll be using is how we can build Bayesian models using PyMC3 for modeling COVID-19. A few words about me. I'm Thomas Wiecki. You can email me or follow me on Twitter. I recently, with a few friends of mine and PyMC core developers, launched a consulting business called PyMC Labs, where we help companies solve advanced analytical problems using Bayesian statistics. If you have such a problem, I'd be very happy to hear from you and work with you. Before I launched this, I was the VP of Data Science at Quantopian, a Boston-based crowdsourced hedge fund. And before that, I did my PhD on computational psychiatry at Brown. And that is also where I learned about Bayesian statistics and got involved with the PyMC3 project. Now, in this presentation, I want to highlight a few key strengths of Bayesian statistics through an applied let's build a model exercise. I hope that the strengths that will shine through in this talk include the flexibility you have with these to build and quickly iterate statistical models. So we will see how with computer code we can just write our models as we see fit and then revise them and improve them in an iterative fashion. And that, I think, is a really powerful approach in doing statistical modeling. Moreover, we have a very principled way of dealing with uncertainty, and this will become clear. At the very core, you can think that basically never do we ever have just point estimates, like a single scalar value for a parameter value, but rather we will always deal with probability distributions. And these probability distributions represent our uncertainty, or a range of parameter values that we deem plausible. Moreover, we don't just want to model the most likely outcome, we want to model a distribution of all possible outcomes. So that is just a different way of saying the uncertainty. The other really powerful concept, something that I think is really important, is that it allows an expert to inform the model. So compare this to, for example, machine learning, where you just give it a whole bunch of data and you hope that the model picks out the right patterns in the data. Well, in most applied cases, you do have a lot of information about the structure and the likely parameter values before even running any model, right? Often data scientists or domain experts have worked with this data many times before, so they sort of know what they want. And here we can now, in Bayesian modeling, use that information to build a custom model that is hand-tailored to the specific problem. So it maps the data generating process or the structure of the data. And moreover, we can then define priors that define certain likely parameter values before having seen any data about what we think the world is going to look like. And in the case of COVID-19, as we will see, we already have a whole bunch of prior information just from published studies, for example. So of course we want to use that to inform our model. So here we learn how we go from data to a model idea, then how do we even find priors for our model, then how do we fit and evaluate a model, then we will identify some shortcomings of that model and iteratively improve upon it. Then we will see how we can forecast in the future, something that is especially interesting for time series models like here. And then we want to take a closer look at generative modeling in the second piece. Now first, we're going to import a whole bunch of modules. Load COVID data is a custom one that I will include in the code as well. So basically that just fetches the data from the WHO. And here you can see I'm just getting the data frame, and it looks like this. So for every country, for every day, we have different types of infections or different types of cases. Here we're just going to deal with confirmed cases, which means you got a positive test result back, and then here's the number of cases confirmed. These other ones over here we're not going to pay attention to. Well, actually, one thing that is going to be critical though is that we only look at countries once they cross 100 cases. So all the data that you're going to see, we're going to just ignore everything that happened before a country had 100 cases. The reason being that we assume that, well, the data was pretty noisy early on. And also it gets around the problem that, well, if a country didn't have any cases for a long period of time, where do we do the cutoff? So that just gets rid of a whole bunch of data problems. And it will become important later in the modeling too. So keep that in mind. And then we also can just offset. So rather than dealing with dates, we can just use how many days since you crossed 100 cases we will deal with. Okay, diving next into the Bayesian workflow, we want to build a model of the spread characteristics. How can we model that in general? And as you'll see, I will start out extremely simply. In fact, so simple that it's going to be a terrible model. But we will see why that is a terrible model and then improve upon it. So that will be the key of this lecture today. Now, one way to do the Bayesian workflow that I like is to first plot the data. That is always a good idea to start with. And then we want to build a model of the data. Once we have that model, before running it on any data, right, we just want to check, well, does it produce the type of data patterns that I know to expect? And towards that goal, we can run what is called prior predictive check. We then want to fit the model to get our posteriors, and then make sure that we actually ran the sampler successfully and assess convergence of our sampler. Then we want to run a posterior predictive check to see whether the data that the model is generating matches the data that we observed. And then finally, probably we will identify some shortcomings with our model, and we want to prove upon it. So this is basically the loop that we will keep going over here today. The country that I chose for this is Germany, and here I'm just taking the first 30 days of the German number of confirmed cases since they crossed 100 cases. And this is what that looks like. So you can see here, early March is where Germany crossed 100 cases, and then it rises very steeply, very quickly. That is the nature of an epidemic. You have explosive growth. And now I invite you to think about this for a second and just say, okay, well, if I came to you now and say, well, model this data, how would you do that? Well, one idea would be that looks like an exponential, right? And certainly this has been also talked about in the literature a bunch, that early on in the process, the spread of the disease follows an exponential distribution. The question is how steep, but nonetheless, because it's an epidemic and one person affects two infect four, or however many people, you get this exponential growth. And that is exactly why why we're having such problems with this pandemic, because of the explosive growth, and why you want to be very early in your lockdowns. So let's build a model for that in pym.C3. This is what that code looks like. The first thing that we want to do is, so I'm just going to rename some variables. So t is going to be the number of days from where we crossed 100 cases, so just 0, 1, 2, 3, 4, 5. And then confirmed is going to be the number of confirmed cases. Now you probably are already familiar with pym.C3 to some extent, but just very briefly, every model will have this with context. And what that does is it instantiates a model and binds it to this variable, and then says, well, everything that happens indented underneath here will be tied to this model object. So it's purely for bookkeeping and for keeping the model concise. Where it gets interesting is in the part below. Our model has two parameters, an intercept and a slope. So basically, the exponential is like a linear regression, but in log space. So we will still have the same parameters, and then we will just exponentiate. The parameters, at every parameter I already said in Bayesian statistics has a prior. So we will assign these prior distributions, which are my belief about this parameter value, about the intercept, without having seen any data. Here we will choose a normal distribution and say that this is called A. So the first argument will always have to be the name. We give it a mu parameter, which is going to be the mean of that normal, and a sigma parameter. So here I'm choosing a normal distribution centered around 0 with a very wide standard deviation. And then the next, for the slope parameter, we also choose a normal distribution, give it a name, and here I'm actually now using the fact that I know a little bit about this disease. So it was said that the reproduction rate is 133%. So basically every 3 days, the amount of cases doubles, is what that says. And then we just plug that into, but we still want to estimate this. So we're just going to center it around that with a pretty wide standard deviation nonetheless. So we allow the model to adjust that parameter, but we're just going to say, well, before you even start, like, it will be somewhere in that range, in that ballpark. And then we just put those together to get our exponential function. So you can just look on Wikipedia and get the formula for that. So a times 1 plus b, so that gets it to 133. And then this is exponentiating with the time dimension. So that's just linear regression in exponentiated. Now here we have the error term for our likelihood function. And here I'm going to use epsilon a half normal, so we know that the variance of the standard deviation can only be positive. So that's why we choose a half normal distribution, which is a normal distribution that is chopped off at 0 and only has positive probability mass. And again, I'm choosing very wide distributions here. The last thing we need is we need to tie these parameters now together with the data. And we do this just like before. We again instantiate a distribution. Here I'm going to say, okay, the number of cases is going to be normally distributed with a certain mean, mu, which is going to be the growth parameter, and a, again, standard deviation parameter, epsilon. So this is going to be the error. And this is going to be the output of that exponential. And now I have to link those together with the data, and we're doing that with the observed keyword argument, where we pass in the numpy array for the number of cases. So this ties everything together. When I execute this, nothing happens. Well, something happens, but it's not going to estimate the model. It's just going to construct the model so far. But before we now push further, I want to invite you to think about, well, is this a good model? Maybe you have some doubts about the exponential, but let's say, okay, the exponential isn't the problem. Are there any other problems with this? Could I have done a better job, for example, with the choice of the priors? So hopefully you have some ideas of how to already do this, but nonetheless, we will go through the exercise with this type of model and just see what happens if we now generate new data from the prior predictive. So the way this works is we just pick a value for A and B from these distributions. So we just sample from those two normal distributions, we apply the math, and then we generate from this normal distribution using the growth exponential that we sampled using these parameters. Then we generate one line from that. And then we do the same thing again. We again sample A and B, and we just do that over and over again. So that is essentially just a prior predictive check. And in pm.Data, you can conveniently just call sample prior predictive, which does all that for you. And now here we're plotting it, and this is what that looks like. So again, we have the number of days since we passed 100 cases, and then the number of positive cases. Now, again, I invite you to think about whether this looks sensible or not. And hopefully it's fairly obvious that this is not sensible at all for several reasons. Well, the most obvious one is that, well, the number of cases can't be negative, right? We can't have minus 50 COVID infected. It's centered at 0. It's floored at 0. And moreover, also, the other problem we see is that the slopes go down. So we know already that we are in an epidemic, so we know that they can only go up, right? Assuming this model. So we're trying to model the early onset of the disease, and it's just not reasonable that I'm expecting negative slopes, which is what's causing this. And another more subtle problem is that because here we're just modeling the cumulative cases, we know that actually that it can't go down. Okay, this is a terrible model. We already see that, but nonetheless, I thought it was instructive to show what happens if you actually try to fit this terrible model now. So here we're calling PM sample with sampler quarks is something I defined up here. This just says, okay, I want to run 4 chains on all my 4 cores, and then this is a keyword argument for sample that will become the default soon, but now we have to supply it, which just returns a new, more powerful trace object or inference data object that we can better deal with. Okay, so now we call sample, and already, so it starts the sample, and then it complains with this remote traceback. And if you have done any modeling whatsoever, you will probably have known and cursed this message because it's quite annoying and it happens quite frequently. But let's look at what happens. So the error that we're getting is, okay, it's a value error that says the mass matrix contains 0 on the diagonal. And then it says also the derivative of the random variable epsilon log is 0 and the derivative of a is 0. Well, this is something that I think we need to improve, but because if you don't really know, it's going to be very difficult for you to debug. Well, the first thing to note is, well, obviously it didn't work, so we need to revise our model. And the mass matrix essentially is estimated during the tuning phase, and it suggests how we want to, which direction we want to move most quickly in with this Hamiltonian Monte Carlo sampler. But there is a problem if we can only estimate this mass matrix from previous samples, and if those previous samples are no good, then we can not estimate this mass matrix correctly. So one trick that you can do to maybe try and see at least what is happening here is to run the sampler but without any tuning, right? Because the tuning is where things break. And then I want to sample 500 without any tuning. So this will not break, right? Because it only breaks during tuning, and I still want to look what the trace looks like. Now I'm plotting this using RVs, plot trace, and you can see that actually here we have the posteriors and here we have the chains. So every sample for intercept and B and epsilon is exactly the same. And we have 2 chains here. So the value never changes. And that is a problem, obviously. And that also says why we can't estimate this. So we want to estimate the variance of this, but the variance if the parameter values are all the same is going to be 0, and that's how we get a diagonal, a 0 on the diagonal of the mass matrix, just very high level. But that's not really all that critical. But you can see, okay, so this doesn't, the samples, but it doesn't ever accept a problem. Now, it's tempting to say, well, these samplers are really brittle. Hopefully we will get better samplers that will just work more robustly. But that is actually false. So these samplers are trying to sell you something different. They're not telling you that they're not effective enough. They're telling you that your model is crap. So this is known as the Folk theorem of statistical computing. If you have trouble sampling, most likely you have a bad model. And I have yet to see a case where that is not true. It can sometimes be quite difficult to do that, but once you get the model correctly, it will sample very well, very fast and efficiently, even in high dimensions. I've seen models with 40,000 dimensions sample in an hour. So, but yeah, it can be tricky to get there. Now, hopefully you already have thought about some problems of this, right? We talked about some of those. So one is the cases can't be negative. Cases cannot start at 0, right? We also know that. I didn't mention this before, but due to the nature that I pre-processed my data, I know that cases can only start at above 100. And they cannot go down. Now let's incorporate that knowledge into a better model. This is exactly the same model, but I just tweaked the priors. I said that the intercept, where we start with the 0 cases, where we start on day 0, is going to be centered at 100. It's actually not always going to be exactly 100, right? Because it could cross from 80 to 120, so then it would be 120 cases on that case. So that's why I still have some sigma around that. And actually, you could still find a better prior here that sort of says 100 is a lower bound, and I only allow it to go higher than that. So you could do that. But for now, let's just go with the simpler version. And the other thing I'm doing here is I'm constraining the prior of sigma to be more narrow around 0.3 because I don't want values that go negative or so many values that goes negative. And then lastly, rather than the normal distribution, which has probability mass below 0, I'm using the negative binomial. And that is a distribution commonly used for counts, which we're dealing with here. And it's similar to the Poisson distribution, which is the more classic one, but it allows a little bit more flexibility because it also allows for a parameter that relates to the variance. And this is called the alpha parameter, and we do give it a prior, which is a gamma distribution. The choice of this isn't really all that important, but it's a reasonable choice in this case. So now let's again sample from the prior predictive and see what we get. Well, this looks way better, right? So it's all going up, it's not starting at 0, and we don't get any negative values. Pretty cool. Now, again, I'm not saying that this is a good model, but it's good enough for now, where we want to fit it and just see how well does it explain the data. Again, we call the sample function, samples very quickly, and now we're going to look at the trace, and you can see, okay, well, this looks quite good. So we have 4 chains, so we get 4 lines here for every parameter, and you can see, okay, well, they all match, so all the posterior chains that we ran converge to the same posterior distribution. That's nice. And we also see that here this looks just like the caterpillar that you're always looking for. So pretty cool. And the other thing I want to note is also, so this basically didn't complain about anything. So usually when there is a problem, we tell you about it. And here, already here we see, okay, nothing seems to have gone wrong. This just further confirms that this seems to look pretty good. And then also we can just plot the summary of this, where we get the means, the standard deviation, and something that you should always look at is the r hat value, which should be very close to 1. And this just says, okay, well, all of these different chains converge to the same distribution. Another thing you can do is plot the energy distribution, which is more technically and related to the Hamiltonian Monte Carlo sampler, how it's proposing different energy levels. So you want the marginal energy to match the transition and energy transitions. And so these distributions should be close to each other. It's not where like one distribution is much wider than the other. So this is a better way to assess model convergence in high-dimensional models, because it's going to be very messy once you have many plots. Here it's not really that important, but I just wanted to point that out, and that's something to look into if that doesn't make sense. It's a very powerful way to assess model convergence. So with these methods now, I'm personally convinced that, okay, well, this went well. I have no reason for concern that this didn't converge to the correct posterior. So I'm going to push forward and going to run a posterior predictive check. Now that is just like a prior predictive check, but rather than just sampling values from the prior and generating data, now we're just picking values from the posterior and generating data. And that will give me a sense of what the model thinks the data looks like after having seen the data. Again, we have this convenient function here called sample posterior predictive, and we just pass it the posterior, and then we can plot this. So now I switch to the log space just because it's easier to see here. So now in log space, an exponential becomes linear. So that's why the red line, which is our data that we observed at the top, that is what the model saw, is basically, looks sort of like a line. And then what the model predicts is, it seems to do a fairly good job. It has, of course, uncertainty around that. There is error around this, but overall it matches this slope here kind of well. Over here, we might be a little bit concerned that now at the top we start to sort of break the model. Maybe that is an issue. You can also look differently and plot the residuals. And this basically, again, confirms that, okay, well, early on it seems to be a pretty good fit. But then as we go further into the future, we see that this does actually diverge, and the error is sort of, there seems to be a systematic bias in the model. So next what I want to do is evaluate the model on data that it has not seen before. And we use that, so basically we want to forecast. And one nice way to do this is to use the pm.Data container. And what that does is it basically acts just like a NumPy array. You can use this object, the resulting object, just like a NumPy array, but you can change the values later. Because what we want to do is we want to fit the model on just the first 30 days, and then we want to evaluate the model using a posterior predictive check on data that is 30 plus more days. And here you can see I also now changed the model to include a bound. We do this because we said, okay, well, there is going to be at least 100 cases, right? There can't be less than 100 cases. So here I can use bound to say, okay, I want to create a new probability distribution that is a normal distribution that has values only higher than 100. I can also do that for the slope, where I say, okay, it should be more than 0 cases. And then this new probability distribution I can just use like I used the normal before. So that's just a quick trick here that I added to make the model a little bit more realistic. But it actually doesn't really change the predictions or anything, so that's not the thing that we're looking for here. So now we sample, and then after we sampled, we have the posterior for the first 30 days. Now we want to simulate those 30 days plus 30 days into the future. So we're going to update our data containers and now pass in the date range from 0 days to 60 days. And then the confirmed cases, we actually also need to update. So remember that we're here just generating data. So at this point, after we fit the data with the model, we actually don't need the data anymore. But nonetheless, we need to make the dimensions in the model work out. So we can't just set this to a different dimension of 60 values, and then basically the model will break if it encounters that here you pass in a vector of length 60 and trying to map that, link that together with data of length 30. So we have to update this data as well, but it doesn't matter with what. It just has to have the same shape. And then again, we sample from the posterior predictive and pass in the posterior. Now again, I'm plotting this on log scale, and here you can see what already we sort of saw happen is that the model, because it's exponential, right, it doesn't know anything about other than that it just keeps gonna go up like crazy, and this is an unrealistic assumption, obviously, right, because the absolute upper limit is the number of people in Germany. More cannot be affected, so definitely there is an upper limit, but the exponential function doesn't know that and can't model that. But in reality, we also know that actually, well, it's not that we're just going to let this thing run rampant, but people react to this. So they change their behavior, and it will level off at some point. And this is what we see in the data once we go out further, and now there is this strong mismatch to the model. So here we confirm, okay, well, it might be a somewhat okay model very early on for just the first couple of days, but then actually it breaks. Which of course good, we want this to break. Otherwise we would be in even more trouble. So how can we improve the model? Well, one very simple thing is to model this with a logistic function rather than exponential. What is nice about this is actually it is very similar to an exponential early on, but then it has a leveling off effect. And so you can see that here there's a carrying capacity which bounds distribution at the top and is it's going to model this effect that at some point there won't be more people infected. Now this should look well, kind of familiar. So again, we have our data objects, our data containers, where we pass in the data for Germany. Now we're going to use the full data. We again have this bounded distribution for our normal. So the intercept is going to be larger than 100. We also have a slope for this logistic function. And now we have a third parameter called the carrying capacity. So how many cases are we going to have? Where's the leveling off effect going to happen? And here I'm just saying, okay, well, it's going to be at least 1,000 people, but it could be also up to 80 million, which is roughly the German population. It's more than that, but that's good enough for now. And then here I'm just transforming the carrying capacity to a parameter that is more natural for the logistic function. So this is what the logistic function looks like. So I'm just following the math, and then I plug that into the negative binomial, which looks just like before. So now simulating from the prior predictive, and again plotting this in log space, we see, well, okay, great. So we get what we're looking for early on as exponential, and then it levels off at 80 million or below that. Now we're going to sample this and then generate posterior predictive sample from using the sample posterior predictive function. And now we just keep that Bayesian workflow alive, right? So the first thing is we build the model again, then we sample from the prior predictive, we sample, now we have the samples, now we evaluate whether our fit is correct. And again, just from first glance, this looks pretty good. You want to look at these other things too that we looked at above, but those are fine too. And now we're going to look at the posterior predictive and see, okay, well, this seems to do a much better job, right? So it doesn't just keep shooting up, but it levels off and it matches the data pretty well. There's a lot of uncertainty around this here. And this is like a skew effect from the way that the logistic sort of blows up in this manner. And we have little knowledge of how this will level off. Here again, I'm just plotting the residual. I guess that's not too much to see, but yeah, you can just see that this looks better and it has that leveling off. Now, one thing that you want to do is you want to compare the models, right? So we already did that in a way, right? So we have the posterior predictive, and that is a great way to compare models with. So just for systematic biases, we can do that, but we can also do something that's a little bit more principled using what is called just the field of model comparison. So for that, I'm just sampling the exponential model on the full data that we used for the logistic model, and then I just call rvs.compare. I give it the name of the model and then the traces for those models. So we only need to pass in the trace. And then it uses a technique called leave one out cross-validation, which is actually not the classic leave one out cross-validation where you keep rerunning the model, just keeping one data point out that you then predict, but rather you are just approximating what you would get if you were to do that. So there's some really cool papers that show that you can just approximate this quantity without having to rerun the model many times. And I'm not going to go into everything here, but you can just see, okay, well, the rank of this logistic model is 0, and so it's better than the exponential, which we already knew, but it's nice to see that confirmed here. And also one thing is interesting is this weight column here, where essentially we could say, well, if we wanted to build the best classifier possible, we might want to average across different models. And this tells us how would we weight those different models to get the best accuracy possible. And here we can see, well, we would actually discard the exponential model and only use the output from the logistic, which makes sense because the exponential model is just so terrible. Now I want to set up the next section and look at another country like the US. So here we can see, okay, again, we have that exponential early on, and then it actually does not seem to just level off like Germany did, but rather it slows down and then it keeps going faster again. So let's nonetheless fit this logistic model and see what that does. Trace looks fine. Let's look at the posterior predictive. And well, okay, so now we see actually this is not a great fit. And well, what is the main limitation of this model? The main limitation is that we assume that time is stationary, that there is no change in the slope or the spread characteristics. We just have one global parameter that describes the thing, the pandemic, but it doesn't show that, well, we have lockdowns, we have people doing social distancing, people started wearing masks, like all of these effects affect this, but our model does not take these time varying things into account. And in the second half of the video, that is the type of model that I want to talk about and show how we can build a model that incorporates all that and is going to be very much more plausible for how this disease progressed. So thank you so much for watching this part, and stay tuned for the second one.